My name's Andrew. I'm not a scientist, I'm a mathematician. And usually when I say that I study math, that gets kind of the same reaction if I said I just punched your grandma. So if that's you, if you're math phobic, then no worries, tune me out. It's a 10-minute talk, just wait for the next guy. But if you got a little bit more patience, then I don't do science even. My math doesn't really have any applications. How exactly do I make this career out of something that people just hate so bitterly, right? Like, what do I even see in it? And I can show you. So back in undergrad, when I was a young warthog, I thought that I got really interested in this field of math that's called number theory, which is the study of the positive whole numbers. So that's, from now on, all my numbers are positive and whole. The positive whole numbers, especially the prime numbers. But I went to this small liberal arts school and it didn't have a class in number theory. So, I thought, oh man, no problem. I went to the library and I dug up this number theory textbook, went off to the second floor, sat down and cracked it open to page 1, right? Because optimal learning strategy, sit by yourself, talk to no one. Write that down, it's a tip. But despite that, right, the first few pages actually went pretty well. It was stuff, that I had sort of picked up along the way as a math major, right? Like, I know what a prime is. I know how many primes there are. I know what we do with primes. Oh. Uh-oh. Oh no. Say view up in the top left, and I believe full screen mode is what I...
Okay, what we did yesterday.
Okay, let's try this. Yeah, that's what I meant. There we go. So, I know that stuff was new to me, but I only made it to page 5 before I absolutely just read headlong into this crazy, wonderful, beautiful problem that I had no idea, never heard of before. And before I share it to you, it kind of needs a little bit of backup or background. The primes are absolutely just totally a mystery. We just don't know. There's some stuff that we can say, especially like global, big, large-scale patterns that we do understand, but there's a lot of things we don't. For example, like this handy-dandy happy birthday balloon. If I hold it like this and take off this orange clip, I can tell you that the air is going to go that way. But the air in this balloon is bounced around at 70 degrees Fahrenheit, right? If you ask me, Andrew, what's going to happen to this particular air molecule right here, which direction is it heading? I don't know. I don't know. They're bouncing around, right? I can tell you on average the air is going that way. I cannot tell you where any molecule is going. And the primes are the same way, that I can say big level things, but I absolutely can't tell you what's small level. So here's a big level pattern. The primes get rarer as they get larger. Out of the first 100 numbers, there's 25 primes. Out of this 100 numbers, there's only 12. But despite that, right, this is a true fact. The primes do get rarer as they get larger. If you hand me a big number, it's very small probability that it's going to be prime. And the gaps between them grow and grow and grow, except sometimes not. Those are as close as 2 prime numbers can get, right? You can't be even in a prime unless you're specifically 2. So primes that differ by 2 like that are called twins. And twin primes appear to persist. There are small ones, there are medium ones, there are big ones, and there are many, many, many more. Which is like nuts, right? Like, how can, I literally just said that they get rarer, except no, they don't. They're close together and far apart. Like, what? What does that even mean? But also, that's also kind of not a surprise with, this physics metaphor that I'm going to make. The primes, right, the individual ones are sort of pseudo-randomly distributed, right? We can't predict them. So I have these lima beans, and now they're pseudo-randomly distributed onto the ground. Some of them scattered, right? But some of them are close together. It's not a surprise that some of the beans piled up, and so it's not a surprise that some of the primes are only twins, only 2 away from each other. And this was first formally stated as the twin prime conjecture in the mid-1800s, that the available evidence seems to suggest that never stops happening, that there are infinitely many such twin primes. That's what I found on page 5. This is so crazy, it's so cool. But it was, everybody seemed to suggest, right, we find these primes and we keep finding them. It appears that it's true, but nobody could prove it. It just sat around for over 150 years till this guy named Zhang, 2013, absolutely came out of nowhere, hadn't published a paper in like a decade. He proved that there are infinitely many primes that differ by n, where n is some number that he couldn't pin down, but it was less than 70 million. Right, which is like a joke. Oh yeah, big help, right? But he proved that that theorems in this area are possible. Like, this is an attackable area, and I can put a finite bound on it. And that was enough to get him a MacArthur Genius Grant, if you've heard of those. And it absolutely set the research community on fire. There's this huge collaborative team of mathematicians that within a year, they'd improved it, found refinements in his arguments, that kind of stuff. They're infinitely many primes that differ by n. They got the 70 million down to 246. And then there's this other related conjecture in the same area that if we add that as one of our hypotheses, you can get it down to 6. And if you would like to become world famous and get a tenure track job at a university of your choice, replace the 6 by a 2. But despite all this just amazing, wonderful, crazy problem, this book that I was reading casually mentioned in less than a single sentence that obviously triplet primes can't happen. There's 3 and 5, that's a twin, but 3, 5, 7, those are triplets. 11, 13, that's a twin, but 11, 13, 15, not a triplet, because 15 factors. What? That killed me. How can twin primes are just so impossibly difficult that if you make 70 million degrees of progress, you get a MacArthur Genius Grant. And triplet primes are just so easy that it doesn't even work out the argument. He just says, oh yeah, sure, clear. How does it even happen? So I shut the book. I had to do a ... because if talking to a scientifically literate audience would kind of give it away. But I shut the book and I tried to figure out what was that reason, what happened. But how do, if you're not familiar with mathematical style argument, what am I supposed to do talking about prime numbers? Am I, take 100 primes and give 50 of them a placebo? How do I even take a sample of prime numbers? There are infinitely many of them. How can I even put a dent in infinity? The idea of experimentation literally just does not even apply to this question. But none of that dumb stuff is going to stop me. And we can do it right now. So here's something that we can say, despite the fact that we're having to stare down infinity and we can't take a sample, here's a true fact. If you divide any positive whole number by 3, you either get remainder 0, remainder 1, or remainder 2. You can't get remainder 3 because that means you're not done dividing, right? And here's the idea I had sitting at this graffiti-covered desk staring at the back of the theater building, is that I can rephrase this using algebra. A number that leaves remainder 0 when you divide by 3, it's a multiple of 3. It's 3 times something. And like we usually do, I've chosen to represent the something with the letter x. And that means if you leave remainder 1, you're 3x plus 1. And if you leave remainder 2, you're 3x plus 2. And once we have got this variable defined and handed, but we can say every number fits in exactly one of these buckets, then it's really easy to see why there's no triplets. One of them has to be a multiple of 3. Let me show you right now. So it's possible that our first triplet is a multiple of 3 itself, right? That's one of our choices. In which case, that's the form that the other 2 triplets take, but who cares because the first one is already not prime. It's also a possibility that our second triplet leaves remainder 1, in which case, look at the other 2 triplets, specifically the middle one. I can factor a 3 out of that, or as I like to call it, not prime. Also, it's a possibility that our first triplet leaves remainder 2, in which case, check out the last triplet. I can factor a 3 out of that one, which makes it not prime. And that's it. We're done. Every single possible number ever fits in exactly one of those categories, and every one of those categories is a problem. There are no triplet primes except for the dumb, trivial starting one, 3, 5, 7. We did it. And when you want to, I felt just so well, pleased with myself. I shouldn't put a good veneer on it, but I just felt so this massive historical problem that was so difficult and had all these books written about it, right? I had taken it and I brought it onto my own doorstep and I had done part of it myself. And now we've done it. And if you personally, each one of you, if you want to do something just startlingly beautiful in math, you don't need a lab, you don't need pipettes, you don't need equipment, you need no machines, you don't need an IRB, nothing. All you need is pen, paper, and an idea, and the pen and paper are optional. So let me leave you with some questions. I just told you that you can do math, so here's some math to do. What happened to 1, 3, 5? I said 3, 5, 7 was the only triplets. Also, another question, our triplets were the 11, 13, 15s of the world. What about the 11, 13, 17s? Any like obvious reasons, why or for or against those? Also, one final question. What happens on page 6? That's it.